Good morning. Welcome to the third of the 3 grade 11 workshops on universal gravitation. I greet you good morning because at the moment now it's 10 to 9. With the public holiday yesterday, we weren't able to have the workshop, so I'm recording it now. So we basically covered all the theory. There's no new theory. We've looked at the universal gravitation law, the statement of it. So I'll just get to that. So by way of quick revision, the law states that every particle in the universe exerts a force of gravitational attraction on every other particle in the universe, and this force is directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers. So mathematically, we represent this law here by this formula. F equals big G. Big G, don't confuse it with little g. Little g is the gravitational field strength at a point in a field, or the gravitational acceleration at the point in the field. It's the same thing, it's just looking at it from different perspectives. But big G is a universal constant. It's the same everywhere in the universe. Well, we're not too sure about inside a black hole, because we don't know much about that, what happens inside there. But big G is the universal gravitational constant, 6,67 times 10 to the negative 11. The M1 and M2 are the masses that are being attracted to each other, and R is the distance between their centers. We can use R or you can use D. Right, we tend to use R when we're dealing with the distance between the center of an astronomical object and its surface, because that is the radius of the planet or the astronomical object. If we're dealing with a point that is not on the surface, well, the distance between the center of it and that point is also the radius, but the radius of an equipotential sphere, an invisible sphere around the center of the astronomical object. So we can use R or D, but the R is there because in actual fact, gravitational field is spherically symmetrical. So the distance between the center to a point can be represented as the radius of a sphere. So we've looked at working out the force between objects of different masses, whether they be small, macroscopic on a scale that we are familiar with, or on an astronomical scale, where we are being attracted to the center of the Earth, or between two astronomical objects like the Moon and the Earth. We've done exercises on that, and then what I did was I gave you this for homework. So we're first going to look at this. We're going to look at working with problems involving force, where we're going to work with, not with values, but with proportionality relations. And then we're going to look at the homework on gravitational field intensity. We'll revise that, as well as some exam questions. So if we look at the homework that I gave you, we're just going to look at this quickly. And generally speaking, these types of problems one finds in multiple choice questions in exams. So I'm going to move it there. So we have two spherical bodies, A and B, with their centers r meters apart. So in the first scenario, we have two objects, A and B. So we've got A and we've got B, and the distance between their centers is r. All right, so now we don't know whether they are, this is not electrostatics, this is gravity. They're always attractive. Whereas with electrostatics, later on in the year, you're going to learn, although at the end of last year, you should have done some electrostatics, that like charges repel and unlike charges attract. But yeah, we're dealing with gravity, purely attractive. So along the line that joins the two centers, there is going to be a force of attraction. And we know that, let's call it force 1. Force 1 is going to be G MA times MB over the radius of the distance squared. Okay, I'm going to call this R1 because this is scenario 1. So there we have an expression for the force that these two objects will exert on each other. It says now, determine the magnitude of the force if the distance between A and B is halved. Okay, so if we look at 6.1, we're going to find that in 6.1, the only thing that's been changed is the radius. And so radius 2 is going to be half of radius 1. So it's going to be radius 1 divided by 2. Right, so therefore F2 will be G, MA, MB, and instead of radius 1 squared, we've got radius 2 squared. Radius 2 squared. But what is radius 2 squared? Well, we've got G, MA, MB, that hasn't changed. Radius 2 squared is radius 1 over 2 squared because the radius, the distance between the two has been halved. So what this results in is G, MA, MB over R1 squared over 4, because 2 squared is 4. But now we're going to tip and we're going to times. But what I'm going to do, I'm going to tip and times, I'm going to bring the 4 to the front. So it's going to equal 4 G, MA, MB over R1 squared. Well, that is just F1. There. So what happens when we halve the distance? We quadruple the force. So determine the magnitude of the force. So therefore F2 will be 4 times F1. All right. Now, these are a more sort of a shorthand to do this in a multiple choice question, which invariably is where it occurs. We know that force is inversely proportional to R squared. So if we halve the radius, then in actual fact, where the change occurs is in the factor with which we have changed the radius, and that's a half, which is basically a half squared is a quarter, tip and times. We've changed the force by a factor of 4. So therefore, force 2 is 4 times force 2 is 4 times force 1. Okay. In a multiple choice question, it doesn't matter which way you've done it. Yeah, so let's look at 6.2. So 6.2 says the mass of body A is doubled. So if we look at 6.2, the mass of body A is now doubled to what it originally was. Right, so this is easier. So force 3 is going to be G, but now mass A, and we need to now maybe put this is now mass A, let's call it mass 3, because let's call this mass 3. So this is going to be G, mass 3 times mass B over the radius squared. Okay, now we must just be careful here. You normally would get these, one of these in a multiple choice. We are continually going back to the original. So when we talk about the mass of body A is doubled, we are now referring back to the original question. So the radius, the distance is now the original distance. It's not following on from the fact that the distance has already been halved. So one just needs to be careful of that we are looking at each of these, determine the magnitude of the force if only the mass of body A is doubled. Okay. So it's not a follow-on. All right, so if we look there, we can say, well, okay, well, we know that mass 3 is 2 times mass A. So this is going to be G, 2 times mass A times mass B over R squared. And so this is going to be, look here, force 3 is going to be 2 times mass A, sorry, 2 times G. G, mass A, mass B over R squared, and this is force 1, so it's going to be 2 times force 1. So force 3 will be 2 times force 1. Okay, so another way of doing this is to say, well, the force is dependent on the product of the masses, mass A times mass B, but if we are only changing mass A by 2, then force 3 equals 2 force 1. So you might say, well, wow, that's just so much easier. It is, if you see it. So in a multiple choice question, you don't have to do it this way. However, if we were to give you a 3 or a 4 mark question and ask you to prove it to us, then you would have to use the algebraic method. All right, let's look at 6.3. 6.3 says both masses are doubled. 6.3, right? So we know that this is force 4, it's going to be G, and now it's going to be 2 times mass A, 2 times mass B over the original distance squared. And so force 4 is going to be 4G mass A mass B over R squared. And the reason is 2 times 2 is 4. So therefore force 4 is going to be 4F1. You could also do it the shorthand way and say, well, the force has been changed by a factor of 2 multiplied by a factor of 2, which is a factor of 4. If we look at 6.4, both masses as well as the distance between them are doubled. Both masses as well as the distance between them are doubled. So if we look at that, we're going to say, and I'm going to do this slightly quicker, we're going to say, so I'm busy with the recording at the moment. Can I come and see you later? Okay. So if we look at 6.4, we can say that force 5 is going to be G, 2 mass A, 2 mass B over double the distance. But now remember, the distance is squared. So therefore, force 5 is going to be G, 4 mass A mass B over 2R squared is 4R squared. But wait a minute, those two 4's cancel. And so therefore, F5 equals G MA MB over R squared. But that's F1. So there's no change. So it seems weird because you've changed all 3 things. You've doubled the mass of one, you've doubled the mass of the other, and 2 times 2 is you've increased the numerator by a factor of 4. The denominator, you've doubled the distance, but remember, it's 2, a factor of 2 squared, so it's 4, and 4 over 4 is 1, so in actual fact you get the same force in a different system. So these kind of questions you find, generally speaking, 9 times out of 10 in multiple choice questions. So now moving on to gravitational field intensity. All right, a gravitational field is a region in space in which a mass will experience a gravitational force. So we've done this before. And in astronomical objects, the gravitational field will be spherically symmetrical. We're not going to deal with some strange object that has got a strange, weird shape, like, for instance, an asteroid that isn't spherical. We're going to deal with spherically symmetrical objects. We've spoken about the fact that the gravitational field strength, which is the force experienced per unit mass, is going to also be proportional to 1 over d squared. Right? So here is the definition of the gravitational field intensity, or the gravitational field strength. At a point, G is defined as the force experienced per unit mass by an object in a gravitational field. So G equals F over M. Okay, if we use F equals G M1, M2 over R squared over M1, for instance, then you get that G equals big G M, and I like to refer to this M as the mass of the source of the field over the distance from its center squared. Right, but notice that if you look at it in terms of Newton's second law, where A equals the net force over mass, well, G can also be viewed as an acceleration. So if you look at this from the perspective of Newton's laws of motion, G is an acceleration. If you look at it from the perspective of field theory, then G is the force per unit mass. Now, I need to just warn you that it's the fact that there's a value for the field at a point does not mean there's a force. You see, in order for there to be a value, in order for there to be a force, force equals mass times gravity. We know that weight, we learned that weight is mass times gravity. If I multiply by m here, F equals mg. You can have a g value there, but that doesn't mean there's a force there. Until you put a mass there, there's no force, even though there's a field strength. So for instance, right at this point here, G equals 9,8, but there's no force. But if I put my calculator there, then there's a force, mass times the gravity constant, the value of the gravitational field strength at that point, times the mass gives me the force downwards. So this here shows us that even though there's no force, there's no mass in the field, as long as you have a mass as the source of the field, you're going to have a value for little g at that point. Even if there isn't a test mass in the field, the source of the field is what creates the field. Right, so finer point, but important nonetheless. So there I proved in the previous lesson the formula for little g, big G m source over distance squared. Right, as I've just mentioned, only time you get a force is if there's a mass in the gravitational field. Right, so these were the questions I gave for homework. Right, so the asteroid Ceres has a radius of 550 kilometers and a mass of 7 times 10 to the 20 kilograms. What would be the acceleration due to gravity on the surface? I'm going to snapshot that. Right, and we are going to take a look at it. Rightio. Okay, so there we go. So Ceres has a radius of 550,000 meters. Okay, so there is Ceres. Okay, it's an asteroid. We're assuming it's spherical. Asteroids are not perfectly spherical. It has a radius of 550 kilometers, but we have to work with distances in meters. Okay, we are told that the mass of Ceres, which is the source, the mass of the source of the field is going to be 7 times 10 to the 20 kilograms. Okay, what would be the acceleration due to gravity on the surface? Okay, so this will obviously have a gravitational field. And so we are going to look at a point on the surface. What will the value of G be? So 1.1. So we're going to say that G, we're specifically looking at the value of G on the surface. G on the surface is going to be big G, mass of the source, which is Ceres, over the distance between the center of Ceres and where we are working out the value for G, which happens to be on the surface, so it's going to be the radius. So that's going to be the radius squared. So G on the surface is going to be 6,67 times 10 to the negative 11. times the mass of Ceres, which is 7,0 times 10 to the 20 kilograms, divided by the radius squared. Now, this is often where learners make a mistake, is when astronomical objects' dimensions are given, for instance, the diameter is given in kilometers, they leave kilometers there. Must always be in meters, and don't forget the square. So we do that. We go, this is 6,67 times 10 to the negative 11 times 7 times 10 to the 20 divided by 550,000, and we square it. And that gives us a value of G on the surface being 0,154 newtons per kilogram, or meters per second squared. Okay. So it's obviously smaller than the Earth, and less massive, so it's got a smaller gravitational field. Right, you'll see the answer there is 0,16. All right, close enough. This is more accurate. We went to 3 decimal places at Parklands College. What would be the Syrian weight of a person with a mass of 90 kilograms? So what they're saying now is, if instead of at the point P, you now put a person. So let's say we now go and we put a person there, and the person has a mass of 90 kilograms. Well, now we're going to have a force, and that force is going to be that person's weight, right? And we don't have to go now and use F equals big G m1 m2 over the radius squared. You can, but you don't need to. What you can do is you can just say F equals the mass of the person times G. So the force is going to be 90 kilograms times 0,154 newtons per kilogram, or meters per second squared. And so if you times by 90, you get 0.154 times by 90. What do we get? We get that the force of that person is 13,86 newtons. And it will be acting along the gravitational field line, acting along toward the center of the Earth. Now, if you want to have weight loss, then you need to go to Ceres, because gravity is stronger, it's weaker there, you're going to have a lower weight. If, however, you want to lose mass, well, you've got to exercise and you've got to diet, because mass is not going to change otherwise. Okay, so that was the first one, all right? You can see here the value is quite different, but that's basically rounding off errors. Don't worry about that. We're really not concerned about that. Okay, next one. Use the following data to calculate the mass of the Earth using G as 10 meters per second squared. Now, you've been given that G is 10. We use G as 9,8. We're going to use G as 10. Radius of the Earth is that. G is that. Okay, you can also see 6,7 instead of 6,67. We're going to use this to get that value. Not that that value is important, okay? But we've been given the values, so we will use the values and just to see the method. All right. There should be no ambiguity about the values of G, big G, in your tests and exams, because you'll be given the data sheet where you use 6,67 times 10 to the negative 11. All right, so looking here, okie dokie, so we take this, right, go down here, okay, and there we go. So now, calculate the mass of the Earth. So what we're going to do, we're going to say, well, okay, G equals big G, mass of the source of the field, which is the mass of the Earth, over the radius squared. Okay, so if you look at the Earth, let's take the Earth, there's the Earth. We are looking at G on the surface of the Earth. The distance between where the center of the Earth is and the point at which we're working out G on the surface, that distance is going to be the radius. Of course, we're making an assumption that the Earth is a perfect sphere, which it's not. It's more bulged at the equator than it is at the poles because of the apparent centrifugal effect, right? And we now know that we have G, we have big G. We're looking for the mass of the Earth. and we do have the radius. They've given us the average radius of the Earth. So we can now go and say, okay, well, what do we have here? We have 10 equals, we're going to use 6,7, because they told us 6,7 times 10 to the negative 11. The mass of the Earth is what we're looking for over the radius squared. The radius is, now be careful here, 6,4 times 10 to the 6 meters or kilometers? Meters. It's fine. It's in the right unit. Don't forget to square. Right, so now what we're going to do, we're going to multiply by this on both sides and divide by that on both sides. So the mass of the Earth is going to equal 10 times 6,4 times 10 to the 6 meters squared, divided by 6,7 times 10 to the negative 11. All right. 10 times 6,4 times 10 to the 6 squared, divided by 6,7 times 10 to the negative 11. And that gives us that the mass of the Earth is approximately 6,113 times 10 to the 24 kilograms. Okay, you'll see that the answer that they've given us is 6,1 times 10 to the 24, but they were rounding off to one decimal place. We round off to 3. All right, so there's an example of how we could work out the mass of the source of a field if given g radius, and we know the universal gravitational constants value. All right, so next, Platinum's Saturn is approximately 90 times more massive and has a diameter approximately 10 times greater than that of the Earth. Calculate the approximate acceleration due to gravity on Saturn. Well, so it's 90 times more massive, but its diameter is 10 times more. So if we look at 3, right, I'm going to take 3 here. I'm going to work with proportionality. Okay, so if we take the mass of Saturn is 10 times the mass of Earth. Okay, sorry, 90 times the mass of Earth, my bad. The diameter is 10 times that of Earth, which means also the radius of Saturn will be 10 times the radius of Earth. The diameter is 10 times, well then the radius will also be 10 times. Okay, so as I calculate the approximate, okay, so now I can tell you now that here, these are old IEB notes. We used in IEB, we used G as 10 meters per second squared. But I'm going to do it with 9,8 meters per second squared. So we're not going to quite get that answer. Okay, we'll get close enough. So we're going to say, okay, so little g on Saturn, this is g on Earth, eh? Little g on Saturn is going to be big G, mass of Saturn, over the radius of Saturn squared. This is going to be G, 90 times the mass of the Earth, over 10 times the radius of the Earth squared. This is going to give us G, going to give us 90g mass of the Earth. Now, 10 squared is 100, RE squared, and that is the gravitational acceleration on Earth. So G Saturn is 90 over 100, which is 9, G Earth, but G Earth is 9,8 newtons per kilogram. So 9 times 9,8 gives us that G Saturn is 8,82 newtons per kilogram, or 8,82 meters per second squared. Now, if we had used G as 10, Okay, then comma 9 times 10 would have given us 9. All right, so there we have a nice proportionality problem. So this, in essence, these are the types of questions you're going to get. There's one other type of problem that I would like you to give it a try, okay? I'm not going to go through it with you. What I will do is I will post the solutions to this. But this comes from a previous exam question, one of my exams actually. Okay, the International Space Station currently orbits the Earth at an unknown altitude. Okay, there it is. Consider the following data. The mass of the ISS is 3,700 kilograms. We can approximate the Earth to be 6 times 10 to the 24 kilograms. The average radius of the Earth is 6,371 kilometers. If the force of gravitational attraction of the Earth on the ISS is 3,22 meganewtons, then determine the average altitude to the nearest kilometer on the ISS above the Earth's surface. So just be careful here. When you're working with the formulas for force and for gravitational field intensity, the R is the distance between the center of the astronomical object and where you're looking at away from it, whether it's on the surface or in space. Okay. Altitude is not the distance between the center and where the ISS is. Altitude is the distance between the surface and where the ISS is. Okay. Just take that. That's a 5 mark. Don't worry about this. Just do this one, 7.2. As I say, I will post the solutions. Please don't look at the solutions until you've actually given this a go. And then typical exam questions. I'd like you to take a look at this one. When I say exam questions, multiple choice questions on this. The magnitude of the gravitational force exerted by one body on another body is F. When the distance between the centers of the two bodies is doubled, the magnitude of the gravitational force in terms of F will now be. Now, my advice to you is to try and do it proportionally. Try not to use the full formulae. Try to work with the factors, as I showed you. And then this one here is another one, 1.8. Two objects of masses 2m and m are arranged as shown in the diagram below. Which one of the changes below will produce the greatest increase in the gravitational force exerted by the one mass on the other? Double the larger mass, half the smaller mass, double the distance between the masses, half the distance between the masses. That's a slightly more tricky problem, but it's also to do with proportionality. And so with that, I leave you with the following. May the force be with you, gravitational force in this instance, and may your test next week go well. And this is really not a difficult section. There's basically only 2 formulas that you need to work with. Just be aware of units, be aware of distance, and that distance doesn't give you altitude, it gives you the center, the distance between the center, or it gives you the distance between the center and wherever you're looking at in the gravitational field. Thank you very much. Have a good day. Bye-bye.